this segment, I'm going to talk about the control of heart rate. The conduction system of the heart is schematized here. We have the SA node located in the upper right quadrant of the right atrium. There are internodal pathways which arrive at the AV, or atrioventricular node, and there are inter-atrial pathways which carry the current from the right atrium to the left atrium. The electrical activity then travels through the AV node, down the bundle of His, and then it branches into the right and left bundle branches, and finally into smaller Purkinje fibers. The AV node has a special property of being slow conducting, and it's this slow conducting pathway that allows the atria to contract before the signal arrives at the ventriculomyocytes, triggering contraction. So the atria can contract before the ventricles contract because we're going through this slow pathway. The sinoatrial node is the pacemaker of the heart under normal conditions. There are reports that the pacemaker can actually be down into one of these internodal pathways. Generally, it's in the sinoatrial node. Here we're going to look at action potentials in the SA and in the AV nodes. The dotted line here represents threshold for voltage-gated calcium channels, and this solid line is the resting membrane potential for sodium channels. Let's begin at phase 4. In phase 4, we see an unstable resting membrane potential for sodium. That is, on hyperpolarization, these sodium channels open. Upon hyperpolarization, sodium begins to leak in, generating a sodium current. And this sodium current continues to rise until we reach threshold. At threshold, voltage-gated calcium channels open, and we see an increase in calcium current. This is phase 0. Phase 1 and 2 are not included here. You'll find those in the ventriculomyocytes. So in this example, we rise above 0 volts, and calcium channels close, potassium channels open, and we get repolarization, and we fall below our resting membrane potential, and our sodium channels open again, and potassium channels close. So the opening of sodium channels gives us our leaking current. The closing of potassium channels allows the system to depolarize. If potassium channels stayed open, as sodium came in, potassium would leave, either there'd be no or little change in membrane potential. These sodium channels, these hyperpolarizing activated sodium channels, I'm calling H channels. The books will often refer to as HCN channels. These are hyperpolarizing activated sodium channels. And some books will even refer to these as funny channels, a term which I don't like to use. So during phase 4, we see leakage. During phase 0, we see the action potential. And during phase 3, potassium channels open and we repolarize, and the system starts over again. And this is just a depiction of calcium channels opening on early depolarization, potassium channels, late depolarization. So this is phase 0, phase 3. And the H channels, or HCN channels, are open on hyperpolarization. So this is just here as a reminder of what I just spoke about. Now, slow conduction occurs, as I mentioned before, between the atria and the ventricles, so that the ventricles will fill with blood from the atria before the ventricles contract. Also, the conduction system has rapid conduction. This allows the activity to spread around the ventricles, causing all the ventriculomyocytes to contract at nearly the same time. In addition, all the myocytes are coupled to their neighbors by gap junctions, and this allows the sodium that caused the depolarization of one cell to pass through the gap junctions and initiate a depolarization of its neighbor. I'm going to put this up here, let you read this at your leisure. What is important is to show that the Purkinje fibers and the ventricles have high rates of conduction. The nodal tissue have very low rates of conduction. And I'll leave this up here. You can pause and read this. This gives you an indication of the rates of depolarization. We say these rates indicate the rate of diastolic depolarization. Very fast in the SA node, slower in the AV node, even slower again in the conduction system. If that SA node fails, the AV node will take over and pace the heart at a slightly slower rate. If both nodes fail, then the conducting fibers can pace the heart at an even slower rate. Intrinsic regulation, that's the regulation that doesn't require any external influence. You can review the Starling's law of the heart in my discussion on the pressure volume loops. However, heart rate is intrinsically regulated by the SA node with the AV node as backup. Beats will occur even if all nerves are severed. Even if the heart is removed from the body, placed in a dish, kept alive, it will continue beating. And here I'm just summarizing some of the extrinsic effects of regulation of heart rate. Sympathetic nerve causes an increase in heart rate. Parasympathetic nerve causes a decrease in heart rate. When you look at the section on contractility, you'll see that the sympathetic nerve causes an increase in contractility. The parasympathetic nerve has almost no effect. A slight bit on the atria because the parasympathetic nerve only stimulates the SA and the AV nodes. As a result, some ACH from the parasympathetic activity can leak out and cause some of the myocytes to decrease their contractility. It is not measurable unless you have highly sensitive equipment. Looking here at the right and the left, we can see that the parasympathetic nerve stimulates both the SA node and the AV node, with the right parasympathetic nerve primarily stimulating the SA node and the left the AV node. The same thing can be said for the sympathetic nervous system. The right sympathetic system stimulates the SA node primarily, the left stimulates the AV node. But in addition, we can see here that the sympathetic nerve sends fibers to the ventricular myocytes. Sympathetic activity can enhance contractility of the myocytes. And once again, look at my discussion on cardiac contractility. This is from a paper I wrote in 1985 with a friend of mine, David Jones. And it was done on a peking duck, but if you look at the latest Byrne and Levy textbook, you will see it's virtually identical to that of a mammal. In this first one, what I did was to stimulate the parasympathetic, the vagus nerve, leading to the heart, and stimulation is occurring during this white bar up here. And what you can notice is within a couple of beats, we're down to nearly the lowest heart rate that this animal can generate. And when we remove the stimulus, within a couple of beats, we're back to normal. In fact, we'll overshoot a little bit and then return back quickly to normal. The parasympathetic nervous system has a rapid influence on heart rate. Stimulating the parasympathetic causes a rapid decrease in heart rate. Removing parasympathetic activity causes a rapid increase in heart rate. Compare that with the sympathetic nervous system. Here I stimulated the cardiac branch of the sympathetic system, and we can see a gradual increase. This takes more than 30 seconds to reach its maximum heart rate with sympathetic stimulation, and when we remove the sympathetic activity, it takes another 30 seconds to come back down, approximately, much slower than the parasympathetic activity. So if you are frightened and your heart rate runs up, it's most likely because the system has removed parasympathetic tone to your heart and your heart rate sped up quickly. And here I'm not going to explain much about this. This is another diagram from a paper in which we can see with minimum parasympathetic tone and maximum sympathetic tone, we reach our highest heart rates, and conversely with maximum vagal or parasympathetic activity and minimum sympathetic activity, we reach the lowest heart rate. And we can adjust the frequencies of both of these and generate this three-dimensional saddle curve. So you can look at this if you wish in greater detail by hitting pause. So how does the sympathetic and the parasympathetic nervous system control this heart rate? We have parasympathetic ACH, acetylcholine, activating an ACH receptor and a G protein here, and I'm showing another one here, and norepinephrine activating a G protein, which then stimulates adenylate cyclase. Let's talk about sympathetic control first. In this example, norepinephrine is stimulated a G protein, which activates adenylate cyclase, which generates cyclic AMP. Cyclic AMP activates a protein kinase. That protein kinase in turn activates this sarcoplasmic endoplasmic reticulum calcium ATPase pump, which is a long way of saying SERCA. This enhances calcium uptake into the sarcoplasmic reticulum, and I'll speak more about this in the contractility talk. Cyclic AMP activates protein kinase A, and in this example, protein kinase A opens up calcium channels, and this is important, again, for contractility. But for controlling heart rate, the important thing is it opens up these H channels, allowing sodium to enter faster than normal. So sympathetic activity opens up H channels, and sodium rushes in at a faster rate. I'll get back to that again in a minute. Now let's look at the parasympathetic activity. ACH stimulates a G protein, which, on the one hand, the G protein opens up potassium channels to generate a hyperpolarized membrane. And it also activates this nitric oxide synthase, which produces nitric oxide. Nitric oxide stimulates guanylate cyclase, and guanylate cyclase, like adenylate cyclase, triggers the production of cyclic GMP, and cyclic GMP stimulates protein kinase G. Now, protein kinase G has the opposite effect, closing sodium channels and closing calcium channels. Cyclic GMP also activates this phosphodiesterase, and it's the job of phosphodiesterase to break down cyclic AMP. So not only are we interfering with the entry of sodium and calcium, but we're also inhibiting that which is going to stimulate opening of these channels. By breaking down cyclic AMP, we slow this process down. ACH not only enhances the breakdown of cyclic AMP, but it directly inhibits adenylate cyclase, thereby reducing the production of cyclic AMP. In this diagram, we can look at the action potentials of a control group, one with sympathetic stimulation, one with parasympathetic stimulation. So here in this middle graph, we can see the slow rise of membrane potential until we reach threshold, action potential, repolarization. If we stimulate the sympathetic nervous system, we see a more rapid rise in membrane potential. Therefore, the action potential is going to come sooner, and then repolarization. If we stimulate the parasympathetic nervous system, we can see the hyperpolarization occurring from potassium leaving the cell, followed by a more gradual rise in membrane potential because of the slowed sodium entry. And now we see the action potential and repolarization. Now let's look at this as a series of beats. Here again we have the control. We see this rise, action potential, repolarize, rise, action potential. In the sympathetic nervous system, a more rapid rise. We reach threshold sooner. Each beat comes closer together. So we see an increase in heart rate, and with parasympathetic stimulation, we see a more gradual rise, and each beat is now delayed somewhat, leading to a lower heart rate. That concludes this talk on the control of heart rate.